Hello, this is the next in my NMR A-level chemistry questions. This question in particular caused more tears and anguish than any past paper NMR question that I can think of. So if you are giving this one a try, I salute you, well done. Okay, so starts off, we're given a compound which is a carbonyl and it reacts with 2,4-DNP and it makes the orange precipitate. This you hopefully recognise as tests for the carbonyl. Now what you are told is that eventually you're going to have to identify the compounds L and K. But before we get there, just a few extra small 1-mark questions. Describe a use for NMR spectroscopy in medicine. N stands for nuclear, meaning the nucleus of an atom, but in medicine people don't like the word nuclear, so what we call it is MRI, which stands for magnetic resonance imaging, and that key bit, the imaging, is for diagnostic reasons, so that's what they want. Just try and make sure you put that extra information in, so to diagnose what's going on inside the body. Okay, state the region of the electromagnetic spectrum used in 1H NMR spectroscopy. So it is radio waves. That's one. It is simply just a fact for you to learn. And explain why CdCl3 is used as a solvent in proton NMR spectroscopy. You need to know that D, deuterium, is hydrogen 2, which has an even number of nucleons, which means that it's not going to show up on your spectrum. So it doesn't show on the spectrum, it doesn't produce a peak, and means that you can't get confused between the chemicals, between the peaks from your actual chemical you're interested in and your solvent. So it doesn't show on the spectrum because there is no 1H in it. Right, next part, you're given a carbon-13 spectrum, and the simple thing here, you're asked how many different carbon environments are there. When you're asked for that, it's a really simple thing. You count the peaks. Don't forget about the ones down here, and there are 14. These two here, you'll notice, have a higher intensity, and it might suggest to us later on, this might come in, that there are two of the environments that have more than one carbon involved. But the key bit for us just now, there are 14 carbon environments. This is going to come into play later on. Right, so you are given this spectrum here, and you are asked to identify this chemical here. What is worth doing is just reading through here, and there is this lovely little snippet here. In the proton NMR spectrum, a hydrogen on a carbon next to this group here, which if we look up, we've got the carbon with the double bond to nitrogen. So if you have a hydrogen on a carbon that's this carbon here, because it's bonded to the C with a double bond to the nitrogen, so these will be in the range 1.6 to 2.2 ppm, and there is one peak in that range there, so we're going to pay attention to that. So what I always try and do is set out the information from the spectrum into a table like this. So there is a peak at 0.7. We're looking for a couple of different bits of information. The integration is given to us. The integration is the number of hydrogens in that environment. So there are 3 hydrogens in this environment, 3 here, 2, 1, and we'll come to that later. So 0.7 has an integration of 3. Again, there's a tolerance of about plus or minus 0.1 for each of these. I've written them in earlier to try and shorten the video. I'm just going to do this pretty quickly now. 3 for the integration there, 2, 1 and 7. The splitting, it's not the nicest spectrum ever, but that is 3 that it's split into. So this is a triplet, this one is a singlet. Apologies about that page number reference, let's get rid of it just now. This, quite hard to see there, but on the paper itself you could spot it was a quartet. This is a broad singlet. And this isn't any of the things that you will have ever seen or looked at from the standard patterns. So what we're going to do is we're going to call this a multiplet. Now the splitting is all about the n+1 rule, where n is the number of hydrogens on the adjacent carbon. So if it's a triplet, that means that n+1 is 3 from the triplet. So to get the number of hydrogens in the adjacent carbon, you simply take away 1. So it was 3, taking away 1 is 2, 1 take away 1 is 0, quartet 4, take away 1 is 3, well it's a singlet so it's again 0, and we don't do anything for the multiplets for this. So we've got the information we need to try and go through the question. So the easiest thing to look for now is your chemical shifts here. They tell you about the environment and you can use the reference from the datasheet. 0.7 is in the RCH range. 1.8 is the information that was given to us in the question. So this HCN. So I'm going to in fact just skip straight ahead and put this down here. There is only one peak in the range 1.6 to 2.2, so this one has to be the one that is responsible. And now we're going to use the integration. There are 3, so this has to be 3 hydrogens there. So maybe we can get rid of that bond and it's just the CH3 that's on there. It tells us that there is going to be no hydrogen on here because it's a singlet, but if we look at the actual molecule that we're trying to get this for, this carbon has a double bond to nitrogen, it's a CH3 there we've now got, and down here, well there's not just a hydrogen because that would make the molecule stop. So what you are ultimately being asked to do is to get the structure of compound L. I've taken the NO2s and the benzene and the nitrogens here and I've put them all straight on to my drawing here because all of this is known. What we've got this time is just 2 R groups to identify. Now it doesn't matter if you pick R1 or R2, I'm going to put it down at the bottom because I've got less space in my own particular diagram there. So, going back to our spectrum, there are 5 peaks, we've used 1 and we've actually worked out there's a CH3 group. The next one to look at, I think, would be this broad singlet here. The reason to look at that is because you've already been given part of the molecule and you know there is a hydrogen directly on a nitrogen. That would fit with this. It's the broad singlet, which is what you get for OH and NH, so that is your NH. Again, it's not just about identifying the molecule, it's about showing you're working for everything. Okay, the next thing, I'm gonna be brave, I'm gonna tackle it. This region here, hopefully, what you all know is that this means that there are aromatic hydrogens. Except 7, well there's only 6 carbons, so this is the part that really threw so many people. 7 is indeed greater than 6. And the really simple and gutting thing for people who panicked when they came across this is it simply means that there must be 2 aromatic rings in this overall molecule. So if we look, we are given that there is an aromatic system here, a benzene base ring here, and there is an NO2 and NO2 in this nitrogen, so there are 3 hydrogens there. The total is 7. So what it tells us is that we must have an aromatic system, and I'm going to put this like this because it can be somewhere. We don't yet know if it goes on the 2nd, the 3rd or the 4th carbon, but we know that there must be an aromatic system and it must have 2 groups on it. Again, if you're panicking at this stage here going what on earth, just stick with it because we're going to see if we can work out the rest of the information. So here we know that there's an integration of 3, so this must be a CH3, and I'm going to underline it to show that's the hydrogen that's responsible. I should have done it there and there. Now, the splitting is a triplet, which tells us that the carbon adjacent to it has 2 hydrogens. So we know that we've got this part of the molecule. Coming down here, we've got a quartet with an integration of 2. So what does this tell us? The quartet tells us that it's next to 3 adjacent hydrogens. Well, we know there's a CH3, so we know that there has to be something next to that. There are an integration of 2, which tells us that there are 2 hydrogens in this environment and it's next to the CH3. So you're always looking for these complementary pieces. You've got the CH2, CH3 with the first peak telling us about the CH3, and now we've got the second peak here telling us it's got an integration of 2, so there's 2 hydrogens, and it's a quartet, it's next to the CH3. But what about its chemical shift? Chemical shift of 2.4 can mean a whole range of things. It could be carbonyl, but we've got no evidence for carbonyl here, or it could be that it's next to an aromatic system, and we've got the chance here for it to be next to an aromatic system. So we know there has to be CH2, CH3. This peak we've taken care of here. We know that the other one is a CH3. So the only thing we've got left is that this carbon must bond onto a benzene based system, an aromatic ring, and there must be a CH2, CH3 that goes on it somewhere. The exact positioning we're going to use the carbon 13 spectrum that we had earlier to help us with. There were 14 carbon environments in total. This is not symmetrical, so there are 6 here. 1, 2, 3, 4, 5, 6 around the ring. We've got 7, we've got 8, and then the CH2, CH3 would be 9 and 10. So somehow we need to get 4 environments out of this ring system here. There are 2 R groups. I've put them both as R here, but they're not the same. One of them is CH2, CH3, an ethyl group, and one of them is, well, this monster. So R1 is not equal to R2. We can have the second R group next to the first, we could have it here, or we could have it opposite. Because they're not the same, there is no symmetry down this, and so this would lead to 6 different environments. This top and bottom half are not symmetrical, so they're not equivalent. Same here, this would be one environment, the one in between, and the one that the second R group is bonded to would be different, and then this side of the molecule is not symmetrical, so yet again there is no equivalence. However, there would be a line of symmetry down the middle of the benzene ring if we put it like this. Looks like the aromatic ring. Don't know why I've tried to start with a 4 there. Let's just put that as a 1. This is not symmetrical that way. The 2 groups are different. So we can go and say that this carbon would have a different environment to the first one. Therefore, these two would not be the same as each other. However, there's a line of symmetry down the middle of the molecule. These two would be equivalent, these two would be equivalent. That would give us the 4 final peaks in here to allow us to get to 14, which would mean that this is the molecule that we are looking for. I'm just going to get rid of the little numbers that I use to help me count up the number of carbon environments so you can actually see the molecule. Again, there are marks for getting that. If you just got the CH2, CH3 on the benzene ring, you only drop 1 mark. And so it's just about trying to go through it all. It looked like there was too much to do, but it's about breaking down and saying, well, I just need something in one R group, something on the other. And there were the 5 peaks. One has to be by the NH. We know that the quartet and triplet with the integrations of 2 and 3 is an ethyl group. It's always a CH2, CH3. This singlet worth 3 has to be a CH3, and then anything down here, you're just looking for it being an aromatic group, and you're looking for the number of environments in it. So, the very final part of the question, the structure of compound K. Compound K is the carbonyl that leads to this, so it's a mark for taking whatever you put here and replacing the nitrogen with a double bond to the oxygen. Thank you very much.